Welcome to the video on Unit 3, which is labeled as Acceleration. This unit, Acceleration, is going to be divided into 4 videos. This first video is going to be an introduction to acceleration and the concept of acceleration. Let's go ahead and look at a graph that we saw last unit. In the last unit, we saw a position versus time graph that looks something like this. Notice the position is changing at a constant rate as time goes on. We can represent this as a linear equation. Now, if you'll notice, we learned last unit that a linear model of a position versus time graph suggests that the object is moving at a constant velocity, since its position is changing at a constant rate per time. However, in this unit, we're going to see that the position is changing not constantly, but instead is going to look something like this. If we were to analyze this graph and look for some trends, we'd notice that the slope is getting steeper as time goes on. For example, the slope right here at 2 seconds is kind of shallow. The slope at 5 seconds is a little bit steeper, and the slope at 9 seconds is very steep. Remember, the slope of a position versus time graph will tell you velocity, and as you can see, since the slopes are constantly changing, that means our velocity is changing. So in this second graph, we can see that the velocity is changing at a constant rate. This is known as acceleration. So what would the velocity graphs look like if we were to graph those two? Well, the velocity graph to the left would look like a straight line. After all, a constant position versus time graph suggests that the velocity would be constant. However, the velocity graph for the right graph over here would suggest that the velocity is actually increasing. Once again, remember, the velocity started out very low and gradually increased as time went on. We would show that by showing the velocity graph as a linear equation. Now, we talked about how the change in velocity is known as acceleration. Acceleration is simply the rate at which velocity is changing. Compare this to the definition for velocity. In Unit 2, we learned that velocity is the rate at which position is changing. So acceleration is just looking at how velocity is changing with respect to time. Another way of thinking about it is that if velocity is changing at all, it is accelerating. For example, if I have an object that starts out going 3 meters per second, then goes to 4 meters per second, and finally goes to 5 meters per second, we can say that it is accelerating. However, let's look at another example. Let's say an object is moving at a constant 5 meters per second, and then decides to turn around and go 5 meters per second the other way. Is the object accelerating? You might be tempted to say no, since the speed is constant. But since the object changed direction, it is accelerating, since velocity is a vector quantity. If the direction changes, the velocity changes. And if the velocity changes, acceleration is constant. So, what would that graph look like? Now, we've already talked about how to get from a position graph to a velocity graph. You take the slope. If we were able to take the individual slopes at all those points and graph them, we would end up getting the straight line that we get here for velocity. In calculus, this is known as the first derivative. So if we wanted to go from velocity to acceleration, we would do the same thing. We would find the slope. After all, a slope is just a rate of change per time. So to find the acceleration graph, we would have to take the slope of this linear line right here. And we know from Unit 2 that when we take the slope of a linear line, it yields a constant value. And therefore, the acceleration graph would look like a positive, straight horizontal line. Notice, I know that the acceleration is positive because the slope here is a positive slope. Now, if you recall from Unit 2, we were able to figure out information by going backwards. Remember, if we wanted to go backwards from a velocity graph to a position graph, we took the area. And the area underneath a velocity graph would tell you some information about the position. For example, the area under this curve, which ends up being a triangle, would end up telling you the change in position, or displacement. The same is true for an acceleration graph. If we wanted to go backwards, we would take the area. Now let's think, what would the area under an acceleration graph tell you? Well, think about it. The area of a rectangle is base times height, or in this case, time, which is in seconds, times the height, which is known as acceleration, measured in meters per second squared. In that case, the seconds would cancel out, at least one of them there, and you'd be left with the units meters per second. This is the units of velocity, and more specifically, it's the change in velocity. So let's review. When you want to find the graph before it, you take the slope. Slope of a position versus time graph will tell you velocity, and slope of a velocity graph will tell you acceleration. If you want to get backwards, the area underneath an acceleration graph is going to tell you change in velocity, and the area under a velocity graph will tell you change in displacement, or change in position. So we get an equation from this. Looking at just my velocity graph and my acceleration graph, we can see that we would get these two lines that are formed. The average acceleration is simply taking the change in velocity over change in time. This is essentially saying, find the slope. Now notice, when you find the slope of a velocity graph, it's rise over run. Well, what would be the units for the rise? The rise is your y-axis, which in this case is velocity, and velocity is measured in meters per second. So the rise value would end up being meters per second over the run. Well, what's the run value? The run is in time, and time is measured in seconds. So we'd end up getting the units for acceleration is meters per second per second. This can get kind of confusing. So we use algebra to get our simplified units of meters per second squared. How we get that is meters per second, which is right here, divided by a second is the same thing as multiplying by 1 over second. Meters times 1 ends up giving you meters, and second times second gives you seconds squared. So the units for acceleration is meters per second squared. Once again, it's just measuring the rate at which velocity is changing. So let's do a little practice first with this idea of acceleration. Remember, an object is accelerating if its velocity is changing. So the question is, determine whether the objects graphed in each separate situation are accelerating or not. In the first one, you might be tempted to say that there is no acceleration. After all, it's a linear line. But notice, you're looking at a velocity versus time graph. And since this is a velocity versus time graph, and we can see as time goes on, the velocity is increasing, this one is definitely accelerating. For the second one is also a linear line, but notice its position versus time. If a position versus time graph has a linear line, that would suggest that it has a constant velocity. And if velocity is constant, it is not accelerating. Therefore, the second situation is not accelerating. In the third situation, notice that this is a velocity versus time graph. The velocity for this stretch and this stretch is not changing. However, right here in this 1 unit of time, the velocity changes drastically. And so, since there is that change in velocity, there is an acceleration, specifically right here at this unit of time. Finally, the last one is a position versus time graph. Notice the position versus time graph stays constant, then all of a sudden drastically changes down. What that means is the slope is drastically getting steeper and steeper as time goes on. And if the slope is getting steeper, that means the velocity is changing. And therefore, yes, this object is accelerating. Now, these are the 4 basic position versus time graphs you will see in this unit. Notice they all represent a parabola or hyperbola, or some sort of ax squared plus bx plus c formula. It's good to recognize these 4 basic types of position graphs, know what direction they're going, and whether they're speeding up or slowing down. Let's take a look at the first one. First of all, I want to notice what direction is the graph going. Is it going away from the origin or towards the origin? Notice the graph is going upwards. That would be known as away or traveling in the positive direction. The question now is the object speeding up or slowing down? Well, let's look at what the slope is doing. Is the slope getting steeper or less steep? You can see the slope is very shallow at the beginning, but then starts to get higher and higher as we go up. If the slope is getting steeper, then that means the object is speeding up, and therefore, the object is speeding up. A quick little way you can remember whether it's speeding up or slowing down is notice that in each of the four graphs, there seems to be an area of the graph where it's leveling off. Or in other words, it looks like it's flat. In our first example, the flat area looked right at the very beginning. Flat areas on a position versus time graph represent a time where it's not moving, or moving very slowly. And so if it's moving very slowly at the beginning, it must be moving faster towards the end. Let's look at the second graph. The second graph is going towards the origin. Notice it's moving downwards towards the origin. So this is going towards the origin, or in other words, we can say it's moving in the negative direction. Now, is it speeding up or slowing down? Well, let's look at what the slope's doing. The slope starts very dramatic at the beginning, but then starts to get a little less steep as time goes on and starts to flatten out right at the very end. If it's flattening out at the very end, what that means is the object must be slowing down. All right, let's look at the third example. Which direction is it going? Away from the origin or towards the origin? We can see very clearly that it is moving up, which means it's moving away from the origin or in the positive direction. Speeding up or slowing down? Well, the object is flattening out towards the end, or in other words, the slope is getting less steep as time goes on, and therefore the object must be slowing down. Finally, let's look at the last graph. The last graph is moving towards the origin, or in the negative direction, and notice that the slopes are getting steeper as time goes on. If the slopes are getting steeper, that must mean it is speeding up. It's a good idea to have these four basic types of graphs memorized so you can recognize the different types of motion. All right, let's do a little practice. I'd like you to look at the animation that's on the screen. Match the car with the appropriate letter on the position versus time graph. So, let's look at the three cars, red, green, and blue. Notice that the blue car quickly passes the red car, and the green car catches up towards the end. If you could block out the green and the blue car, just look at the red. It looks like the red is moving at a constant velocity. So the red car must be corresponding to position B, or graph B, because it's got a linear line, indicating that it's moving at a constant velocity. Now let's just look at the green and the blue. The blue car is the one that catches up to red first. There it is, and then it soon quickly passes. So we know that green and blue are accelerating because they pass the red car. The question is which one accelerates faster? And the answer to that is the blue one. So the blue one is going to correspond to graph A, and the green one is going to correspond to graph C. Notice they're curved graphs indicating that they're speeding up. All right, that leads us into acceleration, which will end this video. Acceleration, remember, is a vector quantity, so it does have a direction, meaning it has a sign. Now, there is one common misconception students make about acceleration. So a lot of students think that if you have a negative acceleration, then that must mean you're slowing down. This is false. This is not necessarily true. Remember, negative is a direction. It has nothing to do with the magnitude of the actual measurement. So negative could just mean it's going north, or maybe going south. That's all that means. So in order to determine the sign of acceleration, it depends on two things. Number one, you have to figure out, is the object speeding up or is it slowing down? Secondly, you have to figure out, is the object moving in the positive direction or the negative direction? Once you know those two things, you will then be able to figure out the sign of acceleration. The rule of thumb, when the object is speeding up, the acceleration is in the same direction of the motion, which is velocity. When the object is slowing down, the acceleration is in the opposite direction of motion, or velocity. So, let's look at an example. Suppose I have this reference arrow on the screen right here. The part on the left, right here, represents where the origin is, and the direction that the arrow points, in this case to the right, represents the positive area. Okay, I'm going to draw a few scenarios up on the board, and we're going to take this rule of thumb that we just learned and put it into practice. Suppose I have an object that is moving to the right. What velocity would you say that it has, positive or negative? The answer is it has a positive velocity since the vector arrows are pointing in the exact same direction that I said is positive, namely to the right. Now, what if I put an acceleration in and I had the acceleration pointing this way? what would be the sign of acceleration? Well, since acceleration is pointing in the opposite direction that I said is positive, it would have to be negative. Now, notice the two signs. Positive velocity, negative acceleration. If they have opposite signs, the object must be slowing down. And therefore, it would be more accurate to say that my object's arrows would look like this. Notice they're slowly getting shorter, indicating that the object is slowing down. All right, what if I did a different scenario? Let's go ahead and draw this in. Let's say now that my object is moving to the right again, so my velocity is going to be positive. But this time, let's say the acceleration vectors are moving in the exact same direction, so acceleration is positive as well. Since both of them are having the same sign, or positive, that means they're helping each other. And so that means the object is actually going to start speeding up, since its acceleration is moving in the same direction as velocity. Now, that was when the velocity had positive direction. Let's look and see, what if I drew this? What if I had an object moving to the left? What would be the sign of my velocity? Velocity would be negative, since the arrows are pointing to the left and I said to the right is positive. Okay, now what if I drew in acceleration vectors like this? My acceleration would have a sign of positive. But notice, since the signs of velocity and acceleration are opposite of each other, that means they're going to oppose one another. And so the resulting speed of my velocity would end up slowing down in the negative direction, because acceleration is actually hurting the velocity vectors. Even though, notice, the acceleration was positive, the object was actually slowing down. Okay, notice in this animation right here, I'm showing the same exact thing. When the acceleration arrows, green, are in the opposite direction of the velocity arrows, blue, the object slows down. But when they're in the same direction, like right here, it speeds up, slows down, wraps around a curve, and then also slows down again. So when acceleration and velocity have the same sign, whether they're both positive or both negative, the object is speeding up. When the acceleration and velocity have opposite signs, they are slowing down. So let's do some practice with this. We're going to do 4 problems right now where I have you asking what is the sign of position, P, what is the sign of velocity, V, and what is the sign of acceleration, A. Notice that I have my reference arrow at the very top, and the moment in time that we're concerned with is the vector arrow that has the red dot. So first of all, what is the sign of my position, positive or negative? Well, my origin is right here, and I'm saying everything to the right is positive. So since my object is right here in time, the position is positive. What's the sign of my velocity? Well, notice all of my vector arrows are pointing to the right, and I said that my right direction is positive. So my velocity is positive. Now ask yourself, is the object speeding up or is it slowing down? Notice that the arrows are getting longer as time goes on. If the arrows are getting longer, the object is speeding up. And if my velocity is positive, my acceleration also has to be positive in order for it to be speeding up. Let's look at this example. First of all, notice that my reference arrow has changed direction. The reference arrow has the origin here, and everything to the left is actually positive. So what would be the sign of my position? My position would actually be negative, since it's starting behind the origin, or in the negative region. What is the sign of my velocity? Notice the velocity arrows are pointing in the opposite direction that I said was positive. In this problem, positive is to the left, but my velocity arrows are pointing to the right. Therefore, my velocity is negative. Now look and see, is the object speeding up? Since the arrows are getting longer as time goes on, that would insist that the velocity is actually getting bigger, or the object is speeding up. If my object is speeding up and my velocity is negative, my acceleration then has to have the exact same sign to be speeding up. And so my acceleration would be negative as well. So you can see how a negative acceleration does not always mean that it's slowing down. We're going to do 2 more problems. What I'd like you to do is pause the video and answer the P, V, and A questions, and then hit resume or play to reveal the answer. All right, in this example, position would be negative, Velocity would be positive, since the velocity arrows are facing right, and right is the positive direction. And since the object is slowing down, it has to have the opposite sign. Therefore, acceleration is negative. Once again, pause the video and do your best to answer this on your own, then hit play to resume. Alright, first question is the position. Position is going to be negative since it starts behind the origin or in the negative region. The velocity is negative because the arrows are facing the opposite direction that I said was positive. And finally, look and see what the object is doing. It's slowing down. If my velocity is negative and the object is slowing down, acceleration has to have the opposite sign, or positive. Alright, last couple of things I want to do in this video is look at some graphs of velocity and some acceleration. Notice on the screen are 4 velocity graphs. What I want you to be able to do is explain what is happening with the object based on each of these velocity graphs. These are the 4 basic types of velocity graphs you'll see in this unit. There are 2 things that a velocity graph can tell you. The first thing a velocity graph can tell you is which direction is the object moving. Is it moving in the positive direction or is it moving in the negative direction? Be very careful on these graphs. These are all velocity graphs. They are not position graphs. And so all these graphs can do is tell you how velocity is changing. So the first question to figure out is it moving away from the origin or towards the origin? Well, if you can see, the 0 mark, it's all right here in the middle. Now, what does 0 correspond to? Does it mean 0 meters? No, remember, it's a velocity graph. So 0 actually means 0 meters per second. So in the middle is when the object is standing still, or at rest. That would mean that the top part of the graph is the positive region, and the bottom part of the graph is the negative region. The first graph has the graph drawn down here. So that means that the velocity during the entire interval of time is negative. What does a negative velocity mean again? Well, negative velocity just means that it's moving in the negative direction, or we like to say sometimes towards the origin. So this velocity is moving in the negative direction. What about the second one? Notice that the second one is drawn up here, which is in the positive region. So the object is moving in the positive region, or sometimes we say away from the origin. In the third graph, notice the graph looks different, but it's still drawn in the positive region. That means the object is moving in the positive region or moving away from the origin. Finally, the last graph is drawn down here. That means that the object is moving in the negative direction, or we sometimes say towards the origin. So we've answered the first question, what direction is the object moving? The second question is the object speeding up or slowing down? Remember, the middle line represents 0 meters per second. So the question you have to ask yourself is the graph moving towards 0 meters per second, or is it moving away from 0 meters per second? If it's moving towards 0 meters per second, it must be slowing down. If it's moving away from 0 meters per second, it must be speeding up. So in the first one, we already know that the object is moving in the negative direction because it's drawn down here. But what is the velocity doing? Well, notice the velocity is getting away from 0 meters per second. So if it's getting away from 0 meters per second, it must be speeding up. But notice it's just speeding up in the negative direction, but it's still speeding up. Let's look at the second one. What is the velocity graph doing? Well, we already know it's moving in the positive direction, but notice the velocity graph is moving towards 0. So if it's moving towards 0, it must be slowing down. In the third one, we've already figured out the object is moving away from the origin again, but notice it's moving away from 0 meters per second. Away from 0 meters per second means that it must be speeding up. And finally, the last graph, it's drawn in the bottom region, which is negative direction, but the object is moving towards 0 meters per second, meaning it must be slowing down. Now, for extra practice, we're going to go ahead and see how this matches up with the position graphs that we saw earlier. All right, on this screen, even though I apologize, it is a little small, on this screen, we've got 5 scenarios of what a cart is doing. I want you to notice what each scenario has. 1, it has a 0 position. The 0 position stands for the origin. Then, notice that it has a cart on a ramp, and it shows you which direction is positive. The positive right here indicates which direction is the positive direction, and I'm highlighting those in all examples. Finally, it has a motion sensor that is going to record what the motion is doing. What we're going to do is we're going to sketch the position graph, the velocity graph, and the acceleration graph for each situation. For situation number 1, we have the cart starting up here, and it's moving down the ramp, which means it's moving away from the origin. What would be the cart's motion? Would it be speeding up or slowing down? Well, hopefully common sense would tell you that the cart would speed up if it was moving down a ramp. So, first question is, what would the position versus time graph look like? Well, it would be going away from the origin, speeding up. So it would be that curve right there. What would the velocity graph look like? Well, since it's moving away from the origin, it has to be drawn up in this region. And since it's speeding up, it's going to have a line going away from 0. Finally, we need to draw the acceleration graph. The acceleration graph, remember, is the slope of a velocity graph. Since the velocity has a positive slope, it must have a positive straight line. Let's do one more. Situation number 2. Notice it says the cart starts down at the bottom, and it says give the cart an initial push up the ramp and stop the cart at its highest point. So the cart is starting at the origin, being pushed up, and it eventually stops at the very top. So it's moving away from the origin still, but it's slowing down. What would that position versus time graph look like? Well, it still needs to go away from the origin, but it needs to level off. So it looks something like this. What would the velocity graph look like? Well, it's still moving away from the origin, so it's going to be drawn in the positive region, but it's slowing down. So my velocity graph would look like that. It would be going towards 0 meters per second. Finally, what is the slope of acceleration? The slope of velocity. Notice the velocity graph has a negative slope, and therefore the acceleration would be a negative line. What I'd like you to do right now is I'd like you to pause the video and try your best on the last 3. Then, when you're ready, hit play to reveal the answers. Alright, the third example has the cart starting away and moving towards the origin, and it would be speeding up. So towards the origin, speeding up would look like that. If it's going towards the origin, the velocity graph is going to be down here, and it's speeding up, so it's going to look like that. It's going to go away from 0. Finally, the acceleration would be the slope of the velocity, which is negative. Also, I want you to notice, before I move on to the next one, I want you to notice when velocity was negative and acceleration was negative, what's the object doing? It's speeding up. Up here on the second one, when velocity was positive and acceleration was negative, what was it doing? It was slowing down. On the first one, when velocity was positive and acceleration was positive, it was speeding up. So the signs are still being consistent. Let's look at number 4. Number 4 is going towards the origin, but it's being stopped at the highest point, so it's slowing down. Towards the origin, slowing down would look something like this. If it's going towards the origin, it's going to be drawn down here, and it's going to be drawn with the line going up to 0, indicating it's slowing down. The sign of my velocity slope would be positive, and therefore acceleration is positive. A negative velocity with a positive slope means that it's slowing down. The last one's a little tricky. The cart starts at the origin, it goes up, stops, and then it comes back down towards the origin. So we're going to actually have a blend of shapes. In the first part of the motion, it goes away from the origin, slowing down. So that would look like this. But then what happens is it goes towards the origin, speeding up, which would look like this. So you actually get a bell curve for your position graph. I'm going to draw a dotted line down the center so we can see how that matches up with velocity and acceleration. Let's look at velocity for the first part. It was moving away from the origin, slowing down. So it would look like this. But then it's moving towards the origin, speeding up. So to continue it on, it would actually look like that. Now notice, even though there's 2 parts, does the slope of the velocity graph ever change signs? And the answer is no, it's always negative. So that means my acceleration graph would be a straight horizontal line in the negative region for acceleration. And that still matches what we said earlier. What's the velocity here for the first part of motion? It's positive, right? What about the velocity for the second part of motion? It's negative. And acceleration's negative for both parts. When acceleration was negative and velocity was positive, what does it do? It slows down. And that makes sense when it's going up the ramp. When velocity was negative and acceleration was negative, that means they're going to be in the same direction or speeding up. And that's when the car was going down. So it still matches everything we've learned. All right, the last part of the video right here is going to go through some sample problems. Notice it's got its reference arrow, and it's got a starting dot. This plus sign right here indicates just where the dot is starting. I want you to notice which direction it's going, is it speeding up or slowing down, and what is its acceleration. And we're going to graph the position, velocity, and acceleration graphs. All right, it's moving away from the origin, speeding up, and so that means the graph should look like this. Notice the position graph swoops up dramatically because its slope is getting steeper. The velocity graph is drawn in the positive region, and it's going away from zero. Finally, the slope of acceleration, the slope of velocity is a positive slope, and that's why the acceleration line is in the positive region above zero. Let's do 3 more. Let's look at this second one. Still moving away from the origin, but the dot is slowing down. So the graph should look like this. The position graph is still going away from the origin, but leveling off. The velocity graph is still drawn in the positive region above zero, but it's going down towards zero because it's slowing down. Finally, the slope of the velocity graph is negative, and that means my acceleration is negative. It's written below the zero. In this example right here, notice the reference arrow is drawn on the right side. That means that the object is actually moving in the negative direction. What is it doing? Well, it looks like it's speeding up. So what would our position first time graph look like? Notice the object is moving in the negative direction, speeding up. If it's moving in the negative direction, velocity is drawn down here, and it is speeding up, so it's getting away from zero. Finally, the acceleration, since my slope of velocity is negative, my acceleration is negative. Last example, the object is moving in the negative direction, but it's slowing down. How does that match up with our graphs? If it's slowing down, the position graph is going to level off in the negative direction. It's moving in the negative direction, so velocity is down here in the negative region, but the actual incline itself is moving towards zero. And since it's moving towards zero and it has a positive slope, my acceleration will be positive as well. This concludes the beginning part of acceleration.